So, for the first lecture, I will just say what I'm going to talk about. Lecture 1. I will introduce real hypersurfaces in Cn. So, real hypersurface in Cn with any n. And I will define, we saw that this morning with Mike, the notion of vector field on M, on a hypersurface. And there I will talk about Cauchy-Riemann vector field, which are special and that reminds under the complex structure in Cn. So it's CR for Cauchy-Riemann, CR vector field, and then exercise. And I was thinking of doing the exercise maybe at the end of the lecture because to have an interaction between maybe some student can come and comment and try to do exercise. Why not? I don't know. We will see how it goes. So, what is a real hypersurface in Cn? So first we are in Cn. So some notation. Z for me is Z1 up to Zn. We have Zj. Each Zj is decomposed like real part plus imaginary part. We have G goes from 1 to n. Xg, Yg are real number. We need also Z bar, which is the conjugate. Z1 bar, Zn bar, Zj bar, obvious, is Xj minus Y, Yj, complex conjugates. I square is minus 1. And now I also have X, which is X1, Xn, and Y, which is Y1, Yn. And also I will need this absolute value of Z square, which is just regular norm square. And we will identify Cn with R2n, right? Z1, Zn goes to X1, X2, Xn, Y1, Yn. It's a normal definition there. So when we will talk about a function, we make without loss of generality, we can write f of x, y, or via the identification, we also write like f of z, z bar, right? Because x nothing, it's z plus z bar over 2, and y is z minus z bar over 2i, right? So we make this, either we write like that, but now we are in Cn with real stuff, we use this kind of notation to remember that we are sitting in Cn, right? So, if n is capital N is equal to 1, so we are back in C, and C, this is a square. So the real hypersurface will be just a curve. You agree? It's a surface. It's going to be something is f of x, right? So we want to mimic that using the structure of C. So that means that we will never be in R3. the next one, C2, is going to be R4. So remember, this is not our subject. We are really in R2L with an even dimension. Okay. So now, the precise definition of a real hypersurface. So remember, we want something like that. So the precise definition. A smooth, we take smooth, we could take CK smooth, just more than C1, more or equal to C, bigger or equal to C1. A smooth, real, this is completely real hypersurface in Cn is a subset called M, such that for every P0 in M, there exists U, a neighborhood of P0, and a smooth real valued function. Real valued function called rho, defined on U such that M, my given M subset, when I intercept with this small neighborhood U, it's exactly U. This is a set of 0. It's a Z living in U such that my function, I use Z bar as I told you, but it's real, is vanishing. This is a 0 set of rho on U, and you can do for any P, you can find it's exactly that. So everything is real, and this is real valued. You could do that for CK, that's not a problem. When rho is real analytic, then we say that the hypersurface is real analytic. But for the time being, I'm taking smooth guys. Oh, sorry. I'm missing the most important. Yeah. Sorry, thank you. You need to have the gradient to be non-zero on U, okay? Such that, thank you very much, such that zero, which is 0, 1 over the x1, 0, etc. at P is different from 0 for every P on U. Okay? Okay? Thank you.
M intersect U is good enough.
M intersect U.
No, I mean the non-vanishing just has to happen on the hypers, but it doesn't matter. This is fine.
Yeah. Is it clear? I think I didn't forget anything. And the vanishing, yeah, it's for every P. It could be for P0, and you just restrict. But this is the most important to have a graph.
Excuse me, if there is a smooth real value function defined on U, satisfy the both conditions. M intersects U and dp.
M is given by rho on U, yeah, with the property that rho has a nice regularity property. That means that the gradient has to be non-zero. D-rho. So it's a real condition on Cn. That's why you need to have this decomposition on Z. Okay? But you can always write this gradient with respect to the Z bar. So but I take the real. Is it clear? So some example maybe to fix the ideas. So what kind of example? Do you know an example? Take C2. What is your first guess for that?
The sphere.
The sphere, right? So what is a sphere? What is the definition of the sphere in higher codimension, in higher dimension? So first example, very important example. Unit spheres in Cn given by the set of Z in Cn such that the summation 1 to n Zj square is equal to 1. Okay? So what is rho here? What is your function rho? Yeah, exactly. Maybe it's trivial, but I prefer it's after lunch, so we have to be. So you just minus 1 is equal to 0. So it's a set of all this guy. The only thing, it's a real function. It's a real function. You just have to check this condition. And so what do? Do you write differently? You write like summation g equal to 1 to n xj square plus yj square minus 1. And I think it's not hard to finish. You choose your, at every point, you choose a point. 1, 0, 0, 0, and you have to do at that point, but you will see that there is no problem. Okay? So check, take 1. You have to do that for every point. Just for this point, you compute the gradient at this point, and you see that there is always 1 which is not 0. Right? Okay, this is the first example. I will give you another example, and then we will show that they are related. It's called the Levi hypersurface. Have you heard about this name? The Levi hypersurface. What is the Levi hypersurface? It's given by the set Levi hypersurface. Is given by M is the set of Z in Cn such that if you take the imaginary part of, say, the last one, it's given by summation Zj square. Right? With j1 to n minus 1. Have you seen that already? Maybe in C2, it's more friendly. You have just ImW is ZZ bar. So again, what is rho? Rho will be Im Zn minus this stuff. Okay? It's equal to 0. You just have to come to see that it's regular. Computing the gradient at every point that leads on the Levi hypersurface, right? Is somebody knowing what is the relation between, is there a relation between the unit sphere and the Levi hypersurface? Somebody knows about that? Biholomorphic? Everywhere? This guy is compact. This guy is not compact. So you have to remove 1 point. Okay, but it's true. I mean, this is an exercise I would like you to do, really to get in an insight of. I will give you exactly what we can see. Where is, yeah. Exercise 1. Exercise. If I give you a rational map. Let h of z, h from Cn to Cn, be the following. It's given by h. This is h. H of z is given the first n-1 component will be, the first one will be I z1 over 1 minus the last one. I z2 over the last one, and you finish always the same, and you go to the last, not the last one, n-1 over 1 minus the n, and the last one will be I Zn plus 1, I guess, over 1 minus Zn. This is a rational holomorphic map, okay? And I would like you to see that exercise. So I give you this map. H sends the unit sphere. Let's call Sn. I will call Sn. I don't know where to put the, yeah, maybe here. Sn. It's here in general, no? Biholomorphically, minus, but I have to remove a point, otherwise it could not be. So say the point 0, everybody is 0, but the last one, it sends to this Levi hypersurface. Sends to the hypersurface IMW is the summation of Zj square, the Levi hypersurface. Okay? Biholomorphically. So you have first to see that there is nothing happening, there is no problem. This is perfectly defined, and so biholomorphically. Is it correct, or maybe I made a, no, I think it's, okay.
It's smaller than capital in C.
What?
You wrote H, Cn to Cn.
What? Yeah, I didn't. Qu'est-ce qu'il y a?
Yeah, it's N.
So, I mean, big N and small. It is only big. That's big N. Big N.
Oh, it's always big.
It's always big. Okay, sir. No, it's just that thing is stretched out. So
Yeah,
it's like small
the
N.
second capital N is
It's a little stretched out.
yeah,
No, above
The
that.
su-
Above that.
yes.
It's okay.
Look, yeah, this just right.
What?
The second capital N in let H from Cn to Cn. Yeah, exactly.
Is it better? No,
It's great.
it's better. So you have to show that it's the sphere is really sends this guy. So there is no problem because you remove the point that is bad, and so it's holomorphically everywhere. So you have to show that it's sent and that the inverse is also of this kind. I think it's a good exercise to do maybe this afternoon at the session if we have time. You have a question? No. Okay. And there is another exercise I would like you to do, which is very important for the talk, for the lecture. Is there something? It's the following. So they are like models, these two guys, for the CR geometry. You can consider it like model hypersurface. Levi non-degenerate, in fact. We'll see that, what it means. There is another exercise I would like you to do. Is the following. For any hypersurface M, for any hypersurface M, and any P naught in M, there exists smooth coordinates x1, I will write like that, up to x2n. This is really real. Near, it's only given near P naught, such that M is given by let's put a prime not to be confused with notation, I prefer. M in this set of coordinates, I made a change of coordinates, and my M can be given by this guy in a neighborhood of P naught. What is the difference with what I talk? The coordinates, they are not holomorphic. They are smooth, they are real. That means that your real hypersurface, you use the reality of the hypersurface. You forget about the CN structure, the complex structure, and you can always flatten it near a point. But that you knew, I guess, in geometry. It's just a real point of view. So there is nothing to do with holomorphy here. But it could be interesting when you do reflection principle. There is some place where it can be useful. So it's an exercise. What do you use for that? Do you have an idea? The? Exactly. It's you choose, yeah, because you need a Jacobian, and then you are set. Okay. And now there is another exercise, which is also important, and then I will leave all this, which is the following. Maybe you know that. When you define your hypersurface, you said there is a row. Is it unique, you think? I could have another row prime, such that M is also the null set of row prime. There is no why it should be unique. How can you characterize all these rows who give the same M? So the answer is here. If row and row prime are, we say defining function. Maybe I should have said that this row, this function in the definition, it's a defining function, right? If rho and rho prime are two defining functions for M, let's say it means that M is given by rho z bar is equal to 0, or M or rho prime of z bar is equal to 0. Okay? M is just the null set of two functions, and they coincide. So what is the relation? It's given just for the null set. But what does it mean? Is there a relationship between R, rho, and rho prime? What do you think? Rho is defined on an open set, not only on M. It's on. So what is how can you pass from rho to rho prime, you think? You have an idea? By a? a non-zero function, exactly. So show, then there exists a non-vanishing, that's important, a non-vanishing real valued, because everything is real valued function. What about the smoothness, you think, if both are smooth? We can take smooth also. Okay? Smooth function called A, such that you pass from rho, it's A times rho prime. Okay? This is a good exercise. And what is the key for that? What do you use? What do you think? How can you prove it? I put the first exercise, the exercise 2 before exercise 3. So, and then you use Taylor expansion. It's the key is always Taylor expansion. That's why you use smoothness. It's in order to use this Taylor approximation. And then that's basic fact. But now is the theorem, which is very important, and that will be used all the time. That means a description. We are looking for a good row in order to do things better. So does there exist a good function such that my M could be described in a good way? So the theorem is the following. Theorem. Sorry without proof, because I will give you a reference. But if I start doing proof, we will never finish. Theorem without proof. And it's not an exercise either, because I think there is enough. So let M be a real hypersurface, smooth, now you know I don't repeat, hypersurface in Cn. At P naught. Then I can find coordinates. What does it mean I can find coordinates? I can make a change of coordinates. Then there are coordinates, holomorphic coordinates. That's very important. We are not interested in smooth coordinates because we want to understand the complex structure in Cn, right? So we are looking for holomorphic change of coordinates. So then there are holomorphic coordinates. Called Z and W. Z, it's going to be now Z1 up to Zn minus 1. And this is going to be in C. We separate the set of coordinates. The Z will be the tangential coordinates, and the W will be the transversal. You will see why. So Z is in Cn. This is n. I call it little n, if you don't mind. So n will be n plus 1. So Z live in Cn, W live in C. W will be always S plus IT. And there is a real, and now a real function, real valued smooth function called phi. Phi, which depends now on z bar. Remember z bar? It's like, and now only on S. It doesn't depend on T. Such that phi of 0 is equal to 0. D phi of 0 is equal to 0. The gradient is 0 of this function. And M is given by W, which is my T, remember. W, which is T, and it's given by phi of z bar S. That means it's a graph. Before it was a row, now we are able to say that it's like a graph T, which is the imaginary part of W. T is a function of phi z bar S. When you were in C, there was no Z. So now you see real, and here leaves the complex, the rest of them. Yes?
It is in Cn minus 1.
Capital A, but let's,
Okay.
I separate the variables, right? So you see why now this is a tangential variable, and W is a transversal because you take T is phi of z bar S. It's like a graph. Etc. Okay? And you can do that, and you can, what is important is to have 0, so P naught is 0, because phi of 0 is 0, so 0 is in M, and the gradient is 0 of this function. Okay?
Excuse me.
Yeah.
M be a real hypersurface in Cn at P0.
At 0.
P0 or at
And I take P0 in M.
Okay, in the result of the theorem,
They are holomorphic.
P0 was appeared.
Around every P naught,
Yeah.
you can find coordinates
Yeah.
such that M can be written as a graph.
P0 but max to
Instead of 0, you should write P0.
Huh?
Here,
Down,
phi
down
of
there.
P of P0.
Phi
Phi
of P0.
Yeah, equal.
Phi of the P naught? No?
Phi of
Yes, I know,
P0.
Yeah.
Yeah, if you want, yeah.
And the
But phi is, yeah.
French.
No, the coordinates, you change coordinates, so P naught becomes 0,
Yeah, yeah.
and in these coordinates,
Yeah.
it's written W. You can always, your rho is given by W minus phi of z bar real W. You see? So to be 0, it means this is like a graph. But it's only local. Why? Because you use always the implicit function theorem. So around every point, you are able to do that using the Taylor series, the Taylor expansion. But you have to be very careful because it's not any, you need the holomorphic version. So it's not that easy. And I can give you the reference if you want.
Sorry. We made, by correcting you, we made a mistake. It's not phi of P0 that makes
No, I know
sense.
it's 0.
No, remove, yeah. It's 0, but
What I mean by local coordinate, you change your
P0
coordinate.
is 0.
You have coordinate with your P0. You go to a different set of coordinates. Your M was there. And now your M here is given by this set of coordinates. And in fact, it's a linear holomorphic change of coordinates. It's not that complicated. So I can give you the reference but you have to deal with the z variable, with linear holomorphic transformation. So I can give you the reference. It's the book by Baruendi, Real Submanifold in Complex Subspace. Real, it's Baruendi, Ebenfeld, Rothschild. And it's a real manifold in complex space, okay? Real submanifold, real submanifolds in complex space. If you want, I can lend to you. I have always it's like a book I always carry with me. Yeah, so I can lend to you. I'm here for 2 weeks, so we can. And I think it's a very nice proof because it gives you the idea how to get into the subject. Okay. So it's always implicit function theorem, but for the holomorphic category, you have to be aware that you have to use a different one. Okay? Okay, other question? So, that's a very important. And so Florian was telling that we didn't do in higher codimension. Here we are in the called hypersurface case. It's an extension. It's a generalization of a surface, but you can consider submanifold because the definition I gave in the beginning, it's embedded. It's a submanifold in Cn, and you can have more than one function. So you have a codimension D. If you have D function, it's going to be codimension D with a Jacobian property non-vanishing. Okay? And in fact, if you do codimension D, that's going to be exactly the same. There is no change. And I will tell you where it starts to be more difficult for the higher codimension case. Up to now, it's exactly the same. Okay? So remember, you have the ball, and you have the unbounded version of the ball minus a point, which is the Levi hypersurface. Okay? Now, we want to understand now the difference between R2n and Cn. So how do we do? Now so we are going to talk about complex tangent vectors and complex tangent fields. What is a complex tangent vector? Okay. What is TPCN? You know what it is? When I write that, knowing that Cn for me is R2n, what is that? A way to write it, so it's for me it's Tp. P is any point in Cn, okay? It's Tp R2n, and it's a set of vector field of the form summation G is equal to 1 to n Aj ddxj plus, remember, Zj is xj plus Iyj, so I don't have to forget any. So plus summation 1 to n bj yj. This is Tp R2n. Now, and yeah, the Ag, for the time being, they are just real number. Okay? It's going to be not real after, but up to now it's real. Now, what is TPM? A way to define TPM. So definition. If P is in M, and X is in T, P, C, N, we say this is an N. That X is tangent to M at P if what? Remember, M is given by rho is equal to 0. What is the definition? Yeah. X apply, this is my X. X applied to rho is equal to 0. No? If summation G is equal to 1 to n aj d rho over dxj, you apply the vector to rho at P bar, you are at P, plus summation Bj d rho over dyj P bar is equal to 0. Okay? This is the definition. And so, to be a good definition, what do you have to check?
Doesn't depend on the coordinates.
Doesn't depend on the row you choose, doesn't depend, exactly. Everything is real, so you are not hoping that you can choose holomorphic. No, you have to, but everything is fine. So, but you knew, I guess, this kind of definition from geometry anyway. But it's a definition we take. But now, we are going to complexify the tangent space because we want the annoying thing. What is the annoying thing? We are living in Cn. But this guy, they are what? They are real. And we don't want real. So you can formally, by using, you know how to complexify a vector space, we allow the aj and bj to be just complex number and doing exactly the same thing. So,
well, strictly speaking, you've already done that on the top line because
yeah.
I mean, you can't really write that expression down because it's not a real vector field.
Yeah.
So
Yeah.
to be real, bj would have to be the complex conjugate.
But I took that, but yeah, it's, yeah.
I know that. Yeah, you're cheating on that. That's right.
So if you put a C in front, CTPCN, now you allow the guy, the AJ and BG become C. Why is it better? What do you think? You want, what do you want? You want, so first remark, I should say that if you, this is TPM, you write this, all the guys who are like that, you write TPM. TPM, it's all this x such that x of rho at P is equal to 0, okay? This is TPM, real. Now you complexify, and in fact you can check that if I take it. What is the dimension of TPM, by the way? You live in 2n minus 1, okay? One less. Cn is 2n real, and you remove 1. So it's 2n minus 1. And what is the dimension of CTPM? The same, right? Just to be sure that it's clear, because you use the same base. It's a way you construct. So it's important to have this notion because you want to see this guy somewhere and this guy, okay? And then to be able to write your stuff with this that gives the structure of Cn, okay? So what is the definition? Maybe I should give the definition. I'm not sure you know everything about this, so just give the definition. What is the time? I have no idea of how it goes. 2h26? Comment 2h26?
You have to compute. I'm bad with 55, I'm bad.
Oh my God, it's almost 1 hour? Mais j'ai commencé à 1h30.
No. I will tell you.
Okay, I will go a little. So, what is the definition of
10
DDZ?
minutes.
Combien?
10 minutes.
So, what is the definition of DDZ? You remember DDZ? What is it? It's 1/2? Minus I. Okay, and DDZ bar, it's 1/2 ddxj plus y plus I dyj, okay? So how can you write? I don't want to see the real everything. Since this guy are complex, I want to write this guy with the zj. How can I write it? So you can check. There's nothing to check. That your x, which is written like aj, can be written now as summation alpha, this is not the A, sure, you have to change it, ddz plus beta j dgb bar and ag bg are in C, right? And now you see that you live in C2n, in Cn. You see? Using these two Cauchy operator, okay? It's not very well written. Can you read it? It's okay. If it's real, if I can always write a guy. What will be the condition to be real? This guy about the alpha j and beta j to be in the real. What is the condition? Yeah? Alpha j and beta j, how are they related? Yeah, conjugate. Sorry. Yeah, I'm a little, I have problem with it. But it's exactly what you said. Yeah, exactly. To be real, alpha j has to be bar of beta j. Okay, and now comes the CR vector field. Up to now, I describe with constant. You see? Tangent space, tangent vector space. But now I could let them vary. P on M vary, and the coefficient varies smoothly. You agree? And then it becomes a vector field on M. So I should say that, and before giving the definition. Now that we are really in Cn, a complex, because now I'm treating only the complex vector field. What is a complex vector field? It's something, a complex vector field on M it's given by X is the summation Aj of P bar, right? It varies with P in M, ddz plus this guy, okay? And P is in M, and Ag, Bg are smooth, complex value, because I did everything, smooth, complex valued function. This is what I mean by complex vector field, which is exactly the same definition we saw this morning. But it's complex. And now I will end with what a CR vector field is. So remember, since it's a tangent vector, that means what? That means if it's a complex vector field, that means that if I apply summation Aj P, P bar, ddz at rho P, P bar, plus beta G P, P bar, ddz bar, rho P, P bar, I should get 0, right? What is your guess now? I want to do holomorphic. Sometimes something magic can happen. There is no Bj. So if Bj is equal to 0, we say that it's a holomorphic. That means it's a holomorphic vector field, because you don't see the bar. It acts like in a, right? There is no z bar, zj bar. The holomorphic vector field. And if Ag is equal to 0, it's anti-holomorphic or CR. Anti-vector field, but also called Cauchy-Riemann vector field. So what is the dimension of this guy, you think? So if I just take a point, huh? If I have summation Aj d rho d z, how many do I have? What is the dimension of this guy? Capital N minus 1, exactly. Capital N minus 1. This is the hypersurface case. What do you use for that? You use that D is that, and that rho is a real function. And that's a big difference with the higher codimension case, because it's no longer, you cannot predict the dimension. It's not n minus d like here. So this is the hypersurface case is easier. And that's the point. So how many minutes left? Nothing?
Between 1 and 2.
So for tomorrow, you just need to, and this guy, I just want to give a name. This CR vector field, which are of this form, it's going to be nu at P, nu P. Nu P is the set of X equal summation, which are tangent. And we will, bar. And tomorrow we'll discuss about properties of that. I'm sorry, but I didn't realize that.
Thank you.